Hi guys, I will start with the intro in strength of materials. Strength of materials is for me one of the most important class in civil and mechanical engineering. Without strength of materials, you will not be capable to do anything further. So you will not be capable to do concrete design, steel design, structural analysis, materials for civil and environmental engineering. So the core for everything in engineering is strength of materials. So let's do some introduction. In statics, we mentioned axial force. So force or load can act on the axis of member, which leads to tension or compression. So if we have force which is pushing toward the member, then we are talking about compression force. If it is pulling, then we will have tension force. For instance, we have connected rod of engine, spokes of bicycles, columns of buildings, tow bar to pull airplane, landing gear of plane, etc. So columns are one of the best example in civil engineering, which is subjected to axial load or axial force. In reality, there will be more than force. Probably you will have some eccentricity, then your column will be subjected also to bending moment. So that is something which we will cover in some other courses. So this is normal force. Normal force act perpendicular to the cross-sectional area. Angle between the forces and longitudinal axis is 0. It tries to changes the axial dimensions of object. Imagine that the member is subjected to tensile force. Then this member will tend to elongate, and this elongation will give us the changes in the length, which will lead to some strains. So that is one example what will happen to a member if it is subjected to tensile force. Then we have a shear force. So shear force act parallel to the cross-sectional area. So angle between the forces and longitudinal axis is 90 degree, and it tries to changes the shape of object. So here is an example. We have two forces which will act parallel to the cross-sectional areas. Example of shear forces. When we are cutting the bread, that is one example of shear forces. When we brush our teeth, again, that is one example of shear force. So here is some homework for you to identify the type of force. So we have columns of buildings, we have elongated spring, we have a scissor, we have crushing failure of can, etc. So this is a homework. So when we talked about forces, we explained the normal and we explained the shear force, but this normal force will give us some normal stress. So what is normal stress? In an externally loaded material, stress is the intensity of internal resisting force which holds each segment of body in equilibrium against deformation, or force per unit area is called stress. So sigma is equal load or force P over area. So units will be Newton over meter square or Pascal or PSI, KSI, megapascals, etc. Stress may remain constant throughout the body or may change from one point to another. So we have direct or normal stress. Stress produced due to normal force acting on a bar. In direct stress, load acts perpendicular to the cross-sectional area of body. For instance, axial stresses, bending stresses, radial or hoop stresses. We have types tensile stress, which will be positive, or compressive strength, which will be negative. So here is one example. what is the normal stress in the bar if we have a force which is 10 kilonewton and we have area 500 millimeters square. So simply we need to divide force with the area and you will obtain the final result. What you have to take care about is the units. So you need to determine if we have kilopascal, pascal, Newton over millimeter square, megapascal, etc. So average normal stress. There is a question, will the total shear force over the anchor length be equal to the total tensile force sigma tensile A in the bar? So we have internal force, we have a cross-sectional area, and we have external force where sigma is equal P over A. Normal shear stress, if we have a coordinate system with X, Y, and Z, then we will have that normal shear stress tau zx is limes when area tends to be equal to 0, delta fx over delta A. Or tau zy is limes when area tends to be equal to 0, delta fy over dA. So we have sigma z, which is normal stress, is force over area, and that is a limes that area tends to be equal to 0. So here is one example. If we have a member which is subjected to forces, so this member has a constant width of 35 millimeters and a thickness of 10 millimeters. We need to determine the maximum average normal stress in the bar when it is subjected to the loading shown. So what we have at point A, we have a tension force of 12 kilonewton. At point D, we have a tension force of 22 kilonewton. So we have at point B and C couple of forces. At point B it will be 9 kilonewton, and at point C we have 4 kilonewton. So width is 35 millimeters. So we have different section will have a different internal forces. Now we need to apply our knowledge from statics. We need to show graphically the normal force diagram. So if we go in a slide, we will see that we have force. If we are cutting between A and B, you will have only force of 12 kilonewton. If you are cutting between B and C, you will have 12 kilonewton plus additional forces of 9 kilonewton, which is 30 kilonewton. Between C and D, you have a force of 22 kilonewton. So your diagram will be 12, then it is jump up to 30, and again it is decreased to 22. So this is the diagram for normal force. By inspection, we need to determine where we have the maximum normal force, and it is between section B and C, which is 30 kilonewton. And we have the same cross-sectional area. Our maximum stress will be sigma BC, which is 30 times 10 on third Newton, over 0.035 times 0.01 when we transfer millimeters into meters. So our final answer will be 85.7 megapascals. Regarding to shear stress, we need to find tau average, which will be shear force over area. Again, we need to determine internal forces and to determine the maximum shear force. So that is the procedure, and we have some example here how to determine the average shear stress in the 20 millimeter diameter pin at A and the 30 millimeter diameter pin at B that support the beam. So firstly, we need to find the internal forces, and after that to apply the equation that tau is equal shear force over area. So again, second homework for you. When we are talking about allowable stresses, we have some safety factors. Safety factors will be the force which will give us the failure over the force which is allowable for us to be used in the system. So that is something which we will use when we start to design. But since this is intro in strength of materials, we can't, or I don't want to go here too much, because we will cover sigma epsilon diagram, which is again for me the most important thing which you will learn or study in strength of materials, and that is something which will be used in all other courses. So here, if we have to design some simple connection, we will use sigma allowable. So again, this sigma allowable will be given to you where you have for a steel profiles, there is a steel codes, and you will read what is sigma allowable for you, depending on the type of profile which you are using. Then we have for shear force requirement, again, area to be determined when we have a shear force, and again, we are using some sigma allowable, which is already given to you using the steel profiles or concrete profiles, etc. So that is the thing which will be given to you when you start to design. Here is one more example. If we have, for instance, rigid bar AB, which is shown here in the figure, and it is supported by a steel rod having a diameter of 20 millimeters, and we have some aluminum block having a cross-sectional area of 1800 millimeters square, the 18 millimeter diameter pins at A and C are subjected to a single shear. If the failure stress for the steel and aluminum is 680 megapascal, and for aluminum is 70 megapascal, and the failure shear stress for each pin is 900 megapascal, we need to determine the largest load that can be applied to the bar. We need to apply a factor of safety which is equal to 2. So here is the solution. The allowable stresses are equal sigma steel failure over safety factors. In our case, we have sigma 680 megapascal for steel in failure. We are dividing by safety factors, which is in this case 2. So your sigma steel allowable will be 340 megapascal. Sigma aluminum allowable is again sigma allowable failure over safety factors. We have 70 over 2, which is 35 megapascal, and we have tau allowable to be tau failure over safety factors, which is 900 over 2, and that is 450 megapascal. So using the system, we will have 3 unknowns. The first one, we have to apply the equations of equilibrium. So when we are finding sum of moment at point B to be equal to 0, we will have a force times 1.25 minus force in the rod AC times 2, that will give us 0. And sum of moment at point A to be equal to 0, so we will have a force at point B times 2 minus force times 0.75 to be equal to 0. So now we need to determine each value of P that creates the allowable stress in the rod, block, and pins respectively. So for rod AC, we have force AC to be sigma steel allowable times area of the rod AC, which is 340 times 10 on 6 times pi times 0.01 on square, which is the area of square, and that will give me the value of 106.8 kilonewton. Using equation 1, our force P will be 106.8 times 2 over 1.25. That will give me the value of 171 kilonewton. For block B, we have sigma aluminum allowable times area of B, which is 35 times 10 on 6 times 1800 times 10 on minus 6, that is 63 kilonewton. Using equation 2, our force will be 63 times 2 over 0.75 is equal 168 kilonewton. So with this example, I want to finish this intro section in strength of material. See you next time. Bye.